title of my talk is Interior Schauder type estimates for AAM's other elliptic equations in weighted Banach spaces. Here you see overview my talk. The abstract introduction, definitions, and auxiliary results. Then I give a statement of the problem and the local existence of strong solutions. Then I will give interior Schauder type estimates, and in last sections we give some examples for the Banach function spaces such as Marcinkiewicz, Grant-Lebesgue, variable Lebesgue spaces. Note that recently works have begun to appear in which differential equations are considered in an abstract formulation. In other words, with respect to some Banach function space defined axiomatically. For example, we consider it as the case of symmetric spaces according to the Luxemburg classification. This class of spaces contains a Lebesgue space, a Grant-Lebesgue space, Orlich space, Marcinkiewicz, Lorentz, and the other spaces. This class doesn't contain Morley space and the Lebesgue space with variable summability index. In terms of Boyd indexes, sufficient conditions are formulated to ensure the validity of interior Schauder type estimates for elliptic operators of AAM's order with respect to Sobolev spaces generated by the norm of the symmetric space under consideration. It is not our goal at this time to provide detailed information about related works. Naturally, the question arises about how far this class of functions can be extended so that this class includes the function spaces considered so far. This work is devoted precisely to solving this problem. This class of functions is also defined axiomatically, namely by definition 1 and the properties 1-3. We will see this a little later in the text of my talk. This class includes almost all previously considered spaces, such as Lebesgue space, Morley, Grant-Lebesgue, Lebesgue space with variable summability index, Orlich, Marcinkiewicz, Lorentz space, and their weighted versions. In what follows, our goal is to consider the solvability problems for now in the strong sense of elliptic equations regarding this class of Banach function spaces. And with your permission, I will follow the presentation. Here you see abstract of my talk. I will read it. We consider the linear uniformly elliptic equations, LO equal to F with non-smooth coefficients in Banach-Sobolev spaces generated by weighted Banach function spaces, some on bounded domain. Supposing boundedness of the Hardy-Littlewood Maximal operator and the Caldeon-Zygmund singular integrals in considered weighted Banach functions, Banach spaces, we obtain solvability in the small in corresponding Banach-Sobolev spaces and establish interior Schauder type a priori estimates. These results will be used in order to obtain Fredholmness of the operator L in correspondent weighted Banach function space. The question of local solvability and the Schauder type estimates play an essential role in the theory of elliptic equations for establishing the Fredholmness of the corresponding boundary value problems regarding appropriate Banach function space. There is a vast number of papers and monographs dedicated to the Fredholmness of partial differential equations in the frame of classical function classes as the Schauder and the Sobolev spaces. The appearance of new function spaces and their intensive study had a very big impact on the regularity and the existence theory for partial differential equations. The so-called non-standard function spaces turned to be interesting not only from theoretical point of view, but also for the applied mathematics and mathematical physics. Among the most studied spaces, we can find the Morrey spaces, the weighted Lebesgue spaces, and the various generalizations, the variable Lebesgue spaces, the grand Lebesgue spaces, the Orlish spaces, and many others. Here you see related works which we list in the reference part of my talk. In the present paper, we are interested on elliptic differential operator of EMS ADA, in weighted general Banach function space with making up type weight W on bounded domain with a smooth enough boundary. In order to obtain the decided a priori estimates, we need that the Hardy-Littlewood Maximal and the Caldeon-Zygmund singular operators are bounded in corresponding weighted Banach function space. Then under certain conditions on the coefficients, we obtain solvability in the small, that is local solvability, in Sobolev spaces generated by weighted Banach function spaces XW of omega. Moreover, we obtain interior Schauder inequalities in weighted Banach function space for the considered uniformly elliptic operators. Such estimates plays an exceptional role in the establishing for the Fredholmness of the corresponding elliptic operators. At the end, we give some examples regarding Banach function spaces. Note that even regarding most of such concrete cases, they obtain results on you. Here you see the standard notations which we use in presentation and also in obtaining mine results. And perhaps I will skip it. And I pass to the following subsections. This is here we give necessary definitions and auxiliary results. The question of existence and regularity of the solutions of linear elliptic equations is strongly related to the question of continuity of certain integral operators in the corresponding function spaces. For this goal, we recall the definition of these operators and introduce the function spaces that we are going to use. First is the very known Hardy-Littlewood Maximal operators. It we denote by F, M, and this is defined by the following formula of 4.1, and the second is the Caldeon-Zygmund type integral operators with characteristic function omega also is defined by the formula of 4.2, and the next is well-known Ritz potential. And then we give a simple one inequality which we use in obtaining my results. This, as usual, is called as Hedberg inequality. So following the monograph 2, we define the Banach function space by Luxembourg classification and give some of its properties. Here we give the corresponding definition of such class of functions. This class is defined by the following axioms. First axiom is as the definition norm. Second is ordered property. Third is the so-called Fatos property. And the next property means that every characteristic of function every measurable set by with finite measure belongs to the corresponding function spaces. And the last property means that in general this Banach function space continuously embedded to the corresponding Lebesgue spaces of summable functions. Here you see the norm of such spaces, and then we give the definition of associated space. It we denote by X prime, and the space is defined by the following formula relation. You see it here, and here we give the Holder inequality regarding such spaces. This is proposition 2. Inequality is 4.5. And let W is some weight function, and then we define the weighted version of considered Banach function space of omega by the following norm. And then we define as usual corresponding weighted Banach-Sobolev space of M's order differential functions by the norm 4.6. And for simplicity, the corresponding spaces we denote by the XWR and etc. when the considered domain is ball with radius R. And here you see the equivalent norm 4.7. This norm we use in obtaining my results. To be able to adapt the classical techniques from the LPCR to non-standard function spaces, we assume that space weighted space XW of omega and the weight function W possess the following properties. Property 1. The first item A means that the above listed operators such as maximal operator and the singular Caldeon-Zygmund operator are bounded regarding to considered weighted Banach function space. And the next item means that there exists such number P0 more than 1 such that this weighted Banach function space continuously embedded to the corresponding Lebesgue spaces with index summability P0. And the property 2 concerns the extension operator. We suppose that omega is bounded with sufficiently smooth boundary, and we suppose that the considered weighted Banach-Sobolev space has the extension property. In other words, regarding such spaces, there exists the following extension operator, which is defined by the conditions here. And the second property we regure is that for a given weighted Banach function space XW of omega, at least one of the following conditions hold. Condition 1, means that there exists such number P1 more than 1, and the positive constant says such that the following inequality holds for every disjoint portion of the domain omega. And the second condition means that there exists such number P2 more than 1, such that the corresponding Lebesgue spaces with index solvability P2 continuously embedding to the considered Banach function space XW of omega. Note that the condition 1 is verified if X omega is usual Lebesgue spaces. And concerning the condition 2, we here give corresponding example. In the case of weighted variable Lebesgue spaces with variable index summability Px with weight omega, I will not read it. You see here. In addition, the classical weighted Lebesgue spaces, note that this weighted Lebesgue spaces with Markov weight verify the properties 1, 3. And it is easy to see that the extension property holds for innovated spaces, just extending the functions as the root of omega. While for the Sobolev spaces, it is not so obvious. This property is well known in the case of classical Sobolev spaces and the weighted Sobolev spaces with the Markov weight. Here you see the related work. These works are 8, 10, 11. We give in the references part. In the other case, asserts that the extension property holds for all K. And the next subsection is statement of the problem. You see here elliptic operator M's order 5.1, and we suppose that this operator is uniformly elliptic. This means the fulfillment the condition of 5.2. And we here suppose that this operator has at the point x0, at the some point x0, the x px0 property if the following conditions hold. This is the px0 condition. It means that the principal, in general, in principal coefficients have limits at this point, of course, are measurable, and other coefficients just bounded. And here you see the corresponding tangential operator, so-called. Here, and then we demonstrate the main properties of the singular kernels generated by the fundamental solution of the considered tangential operator with constant coefficients. These are the properties 5.4. This property provides us the M's order derivatives of fundamental solution corresponding to the tangential operator or Caldeon-Zygmund kernels. And then we define some operators according to the classical case. This we denote by Sx0. This is in general this is the potential risk potential, and the Tx0 operator. And here we give some properties of such operators. And using the boundedness of the singular Caldeon-Zygmund operators and some properties of the risk potential, we establish the validity of the following lemma. My lemma, let's say property 1 and the condition P(x0) hold at some point x0. If the function phi has a compact support in the ball with radius at the point x0, then the operator Tx0 is bounded, and moreover the norm of this operator tends to 0 when the radius tends to 0. And then we give also, according to the classical case, the following lemma. This is lemma 5. Let the conditions 5 to 0.2 P(x0) property, the property 1 and the extension property hold true in the ball. Then the following identity is true for all phi from the corresponding weighted Banach-Sobolev space, and if for some f from the considered weighted Banach functions f, it holds the following equal to, then phi is a strong solution of the equation L phi equal to f. And using these lemmas, we prove the following theorem. Let condition 5.2 property P(x0) and the properties 1 and 2 hold. Then the equation LO equal to F admits a solution in weighted Banach-Sobolev space of ball with radius at point x0 for all f from the corresponding weighted Banach function space for enough small enough radius R. And the next subsection is the interior Schauder type estimates. Our goal now is to obtain local interior Schauder type estimates for the solutions of equation L phi equal to F in the considered weighted Banach-Sobolev space. And for this purpose, according to the classical scheme, we need some auxiliary lemmas. Here you see the necessary notations and functions which we use. And regarding such weighted spaces, we firstly establish the validity of the following lemma 7. Let the conditions of theorem 6 be fulfilled in the ball with radius R2, then for any R1, and for n function U from the corresponding weighted Banach-Sobolev space, the following estimate holds, where the constant C doesn't constant C independent of R1, R2, and U. And in obtaining my results, namely for in establishing interior Schauder estimates, we also use the following lemma 8. This for means that if one of the conditions, one or two holds, then for in a positive epsilon, there exists a number p more than one, and the constancy is such that the following inequality holds, where the constancy doesn't depend of epsilon and O, of course. And using all of these results, previous results, we prove the following theorem. My theorem we consider let L is the uniformly elliptic operator. We consider the equation on the bounded domain with continuous principal coefficients, and other little coefficients are just bounded. Suppose that the properties 1 and 2 above hold, then for on a subdomain omega 0, which belongs to domain omega, the following a priori estimate holds. Regarding to such considerate weighted Banach functions and the Banach function space and the Banach-Sobolev spaces. And in the last section, we recall, we give some examples. Firstly, we prove the following lemma. This lemma means that if we weighted Banach-Sobolev space for fixed K has extension properties, then for all K also there is corresponding extension operator. And we then consider special cases of for Banach function spaces. First example is the Marcinkiewicz space. This space is defined by the following norm. This space here, the supremum is taken overall measurable set here from domain omega, and this space is symmetric but not non-separable. And for establishing validity of the corresponding results regarding such spaces, firstly we must check the fulfillment of above properties regarding such spaces. And for this goal, we use the known results such as Boyd's theorem regarding symmetric spaces. Here we give firstly firstly we calculate the Boyd indexes of Marcinkiewicz spaces. In principle, this are known. This Boyd index are equal to the following quantity: 1 minus lambda divided p. And then we use the following Boyd's theorem. This means that if X is symmetric spaces, then every linear or quasi-linear operator of P, Q, Q joint weak type is bounded in considerate symmetric spaces if and only if the Boyd indexes of this space satisfies the following inequality. And then we property 2 can be proved analogously as in the case of Murray space. and hence a result using these facts, we can obtain from the my results the following corollaries. Corollary 13 concerns the small solution under the condition of theorem 20 z-axis function from the corresponding Sobolev Marchinkiewicz space, which is the solution of the equation L equal to F for all F from the Marchin when the parameters of this space satisfies the following conditions. And the following concerns interior Schauder type estimates. You see here each. And the following, we consider grandly big spaces. This space is defined by the following norm. This space also is symmetric, but also is non-separable. As above, we again use the corresponding results concerning the symmetric spaces. And the Boyd index of such spaces also are known. It is the Boyd index of such spaces equals to 1 divided P, and using the corresponding results concerning symmetric spaces and the boundedness of operators above in these spaces, we obtain the following corollaries. Corollary 15 concerns the small solution. I will not read it. And the following is the interior Schauder type estimates regarding such spaces. And the following, we consider variable Lebesgue spaces with variable index summability index P equals. This space is defined by the using the following modular and by the following so-called Minkowski functional. You see it here. And we consider namely weighted case of such spaces. We firstly review that the summability index satisfies the following log condition. And we use also the so-called Mackenhaupt type class regarding such spaces, which we denote by RPX. This is definition. This class is defined by the following definition. You see it here. And then we use corresponding results concerning the boundedness of above operators such as maximal operators, singular Caldeon-Zygmund singular operator, and the existence of extension operator, and related concerning results one can see, one can get from the monographs, for example, Cruz Ruby. You see here, and using these results, we from the AAM results obtain the validity of the following corollaries. Corollary 19 concern again the small solvability regarding such weighted variable Lebesgue Sobolev spaces. And the following, we also give corresponding theorem from the book Kruse-Rübe concerning the existence of extension operator for fixed K, and using the above lemma, which you have proved, and then we get the validity is the following corollary, which concerns the Schauder type estimate regarding such spaces. And then you see related works. I will show you it. And I finished. Thank you for attention.